Section 1 Introduction. We're going to talk about large language models, LLMs, which are becoming increasingly common and are used in a variety of applications, such as chatbots, document summarization, code completion, and question answering. The full potential of these models can be realized if they can efficiently generate long sequences. For instance, an ideal chatbot should be able to handle day-long conversations. However, it's challenging for these models to handle longer sequences than they were originally trained on. This is because they are limited by the attention window used during training. Despite efforts to increase this window size, there's still a limit to the sequence length they can handle, which restricts their use in long-term applications. In this paper, we introduce the concept of streaming applications for LLMs and ask if it's possible to use these models for infinite-length inputs without compromising efficiency and performance. Two main challenges arise when using LLMs for infinite input streams. First, during the decoding stage, transformer-based LLMs store the key and value states, KV, of all previous tokens, which can lead to high memory usage and increased decoding time. Second, existing models have limited ability to handle sequences longer than the attention window size set during training, leading to performance degradation. One approach to address these challenges is window attention, which maintains a fixed-size sliding window on the KV states of the most recent tokens. While this ensures constant memory usage and decoding speed, the model fails once the sequence length exceeds the cache size. Another strategy is the sliding window with recomputation, which rebuilds the KV states of recent tokens for each generated token. Although this approach performs well, it's significantly slower due to the computation of quadratic attention within its window, making it impractical for real-world streaming applications. We've observed an interesting phenomenon in autoregressive LLMs. A large amount of attention score is allocated to the initial tokens, regardless of their relevance to the language modeling task. We call these tokens attention sinks. Despite their lack of semantic significance, they collect significant attention scores. This is due to the softmax operation, which requires attention scores to sum up to 1 for all contextual tokens. Therefore, even when the current query doesn't have a strong match in many previous tokens, the model still needs to allocate these unneeded attention values somewhere so it sums up to 1. Initial tokens often serve as attention sinks because they are visible to almost all subsequent tokens due to the autoregressive nature of language modeling. Based on these insights, we propose StreamingLLM, a simple and efficient framework that enables LLMs trained with a finite attention window to work on text of infinite length without fine-tuning. StreamingLLM takes advantage of the fact that attention sinks have high attention values, and preserving them can maintain the attention score distribution close to normal. Therefore, StreamingLLM simply keeps the attention sink tokens KV, with just 4 initial tokens sufficing, together with the sliding windows KV to anchor the attention computation and stabilize the model's performance. With StreamingLLM, models including Llama 2, 7, 13, 70, B, MPT, 7, 30, B, Falcon, 7, 40, B, and Pythia, 2.9, 6.9, 12, B can reliably model 4 million tokens, and potentially even more. Compared with the only viable baseline, sliding window with recomputation, StreamingLLM achieves up to 22.2 times speedup, realizing the streaming use of LLMs. We also confirm our attention sink hypothesis and demonstrate that language models can be pre-trained to require only a single attention sink token for streaming deployment. Specifically, we suggest that an extra learnable token at the beginning of all training samples can serve as a designated attention sink. By pre-training 160 million parameter language models from scratch, we demonstrate that adding this single sink token preserves the model's performance in streaming cases. This stands in contrast to vanilla models, which necessitate the reintroduction of multiple initial tokens as attention sinks to achieve the same performance level. There has been extensive research on applying LLMs to lengthy texts, focusing on 3 main areas: length extrapolation, context window extension, and improving LLM's utilization of long text. However, progress in one area doesn't necessarily lead to progress in the others. For example, extending the context size of LLMs doesn't improve the model's performance beyond the context size, and neither approach ensures effective use of the long context. Our StreamingLLM framework primarily lies in the first category, where LLMs are applied to text significantly exceeding the pre-training window size, potentially even of infinite length. We do not expand the attention window size of LLMs or enhance the model's memory and usage on long texts. The last two categories are orthogonal to our focus and could be integrated with our techniques. Length extrapolation aims to enable language models trained on shorter texts to handle longer ones during testing. A predominant avenue of research targets the development of relative position encoding methods for transformer models, enabling them to function beyond their training window. One such initiative is rotary position embeddings, ROPE, which transforms the queries and keys in every attention layer for relative position integration. Despite its promise, subsequent research indicated its underperformance on text that exceeds the training window. Another approach, alibi, biases the query key attention scores based on their distance, thereby introducing relative positional information. While this exhibited improved extrapolation, our tests on MPT models highlighted a breakdown when the text length was vastly greater than the training length. Current methodologies, however, have yet to achieve infinite length extrapolation, causing no existing LLMs to fit for streaming applications. Context window extension focuses on expanding the LLM's context window, enabling the processing of more tokens in one forward pass. A primary line of work addresses the training efficiency problem. Given the attention to computation's quadratic complexity during training, developing a long context LLM is both a computational and memory challenge. Solutions have ranged from system-focused optimizations like flash attention, which accelerates attention computation and reduces memory footprint, to approximate attention methods that trade model quality for efficiency. Recently, there has been a surge of work on extending pre-trained LLMs with ROPE, involving position interpolation and fine-tuning. However, all the aforementioned techniques only extend LLM's context window to a limited extent, which falls short of our paper's primary concern of handling limitless inputs. Improving LLM's utilization of long text optimizes LLMs to better capture and employ the content within the context rather than merely taking them as inputs. As highlighted by previous research, success in the previously mentioned two directions does not necessarily translate to competent utilization of lengthy contexts. Addressing this effective usage of prolonged contexts within LLMs is still a challenge. Our work concentrates on stably harnessing the most recent tokens, enabling the seamless streaming application of LLMs. Section Summary. Large language models, LLMs, are powerful tools for natural language processing tasks, but they struggle with generating long sequences of text. Existing approaches like window attention and sliding window with recomputation have limitations in terms of memory usage and computational efficiency. In this paper, we propose StreamingLLM, a framework that leverages attention sync tokens to enable LLMs to work on infinite-length inputs without fine-tuning. StreamingLLM achieves significant speedup compared to existing methods and demonstrates that a single attention sync token can be pre-trained for streaming deployment. Section 3. StreamingLLM. In this section, we'll discuss the limitations of the window attention technique and introduce the concept of attention syncs. We'll also explain how these concepts led to the development of StreamingLLM. The window attention technique, while efficient, leads to a high level of complexity in language modeling, making it unsuitable for use in streaming applications. To understand why this happens, we'll use the concept of an attention sync. When we look at the complexity of language modeling on a text with 20,000 tokens, we see that the complexity spikes when the text length exceeds the cache size. This is due to the exclusion of the initial tokens. This suggests that these initial tokens are important for maintaining the stability of language models, regardless of how far they are from the tokens being predicted. We can visualize this by looking at attention maps from all layers and heads of the Llama 2 to 7b model. We see that the model consistently focuses on the initial tokens. If we remove these initial tokens, we remove a significant portion of the denominator in the softmax function, which is used in attention computation. This leads to a significant shift in the distribution of attention scores. There are two possible reasons why the initial tokens are so important in language modeling. One possibility is that their semantics are crucial. The other possibility is that the model learns a bias towards their absolute position. To test these possibilities, we conducted experiments where we replaced the first 4 tokens with the line break token, n. We found that the model still significantly emphasizes these initial line break tokens. This suggests that the absolute position of the starting tokens is more important than their semantic value. To explain why the model focuses so much on the initial tokens, we introduce the concept of an attention sink. The softmax function prevents all attended tokens from having zero values. This means that some information from other tokens must be aggregated across all heads in all layers, even if the current embedding has enough self-contained information for its prediction. As a result, the model tends to dump unnecessary attention values to specific tokens. We've observed that language models are typically trained to use multiple initial tokens as attention sinks rather than just one. For example, introducing 4 initial tokens as attention sinks is usually enough to restore the model's performance. However, adding just 1 or 2 doesn't fully restore the model's performance. We believe this is because these models were not trained with a consistent starting token across all input samples. We propose that by including a stable learnable token at the start of all training samples, it could act as a dedicated attention sink, eliminating the need for multiple initial tokens to ensure consistent streaming. We'll test this hypothesis in the next section. Section Summary. The failure of window attention in language modeling is due to the exclusion of initial tokens, which leads to a significant shift in the distribution of attention scores. The model disproportionately focuses on these initial tokens, regardless of their semantic relevance, because they serve as attention sinks. By incorporating a stable learnable token at the start of all training samples, it could act as a committed attention sink, eliminating the need for multiple initial tokens. Section 3.2 Rolling KV Cache with Attention Sinks. In this section, we introduce a simple method to enable streaming in pre-trained language models, which we call the rolling KV cache with attention sinks. This method allows us to maintain the complexity of window attention without needing to fine-tune the model. The idea is to include a few initial tokens in the attention computation along with the current sliding window tokens. We can think of the KV cache in our StreamingLLM as having 2 parts. 1. Attention sinks, which are the first 4 tokens that help stabilize the attention computation. And 2. Rolling KV cache, which keeps the most recent tokens that are important for language modeling. Our StreamingLLM design is flexible and can be easily integrated into any autoregressive language model that uses relative positional encoding, such as ROPE and Alibi. When calculating the relative distance and adding positional information to tokens, StreamingLLM focuses on positions within the cache rather than those in the original text. This is important for the performance of StreamingLLM. For example, if the current cache has tokens 0, 1, 2, 3, 6, 7, 8, and is decoding the 9th token, the positions assigned are 0, 1, 2, 3, 4, 5, 6, 7, not 0, 1, 2, 3, 6, 7, 8, 9, which would be the positions in the original text. For encoding like ROPE, we store the keys of tokens before applying the rotary transformation. Then, we apply position transformation to the keys in the rolling cache at each decoding phase. For Alibi, the process is more straightforward. Here, we apply a continuous linear bias instead of a jumping bias to the attention scores. This way of assigning positional embedding within the cache is crucial to StreamingLLM's functionality, ensuring that the model operates efficiently even beyond its pre-training attention window size. We also discuss pre-training language models with attention sinks. We found that the model's excessive attention to multiple initial tokens is due to the lack of a designated sink token to absorb excessive attention scores. As a result, the model unintentionally designates globally visible tokens, mainly the initial ones, as attention sinks. One possible solution is to intentionally include a global trainable attention sink token, which we call a sink token. This token would serve as a storage for unnecessary attention scores. Another solution could be to replace the conventional softmax function with a variant that does not require the attention scores on all contextual tokens to sum up to 1. We call this method zero sync. To validate these methods, we pre-trained 3 language models with 160 million parameters from scratch under identical settings. The first model uses the standard softmax attention, vanilla. The second replaced the regular attention mechanism with softmax off by 1, zero sync, and the third prepends a learnable placeholder token, sync token, in all training samples. Our results show that while the zero sync alleviates the attention sync problem to some extent, the model still relies on other initial tokens as attention sinks. Introducing a sync token is highly effective in stabilizing the attention mechanism. Simply pairing this sync token with recent tokens sufficiently anchors the model's performance, and the resulting evaluation perplexity is even marginally improved. Given these findings, we recommend training future language models with a sync token in all samples to optimize streaming deployment. In our experiments, we evaluate StreamingLLM using 4 prominent recent model families: Llama 2, MPT, Pythia, and Falcon. Llama 2, Falcon, and Pythia incorporate rope, whereas MPT employs alibi, 2 of the most influential position encoding techniques in recent research. We benchmark StreamingLLM against established baselines such as dense attention, window attention, and the sliding window approach with recomputation. In all subsequent experiments with StreamingLLM, we default to using 4 initial tokens as attention sinks unless stated otherwise. We first evaluate StreamingLLM's language modeling perplexity using the concatenated PG19 test set, which contains 100 long books. For Llama 2 models, the cache size is set at 2048, while for Falcon, Pythia, and MPT models, it's set at 1024. This is half the pre-training window size chosen to enhance visualization clarity. Our results show that StreamingLLM can match the Oracle baseline, sliding window with recomputation, in terms of perplexity on text spanning 20K tokens. Meanwhile, the dense attention technique fails when the input length exceeds its pre-training window, and the window attention technique struggles when the input length surpasses the cache size, leading to the eviction of the initial tokens. We further demonstrate that StreamingLLM can reliably handle exceptionally extended texts, encompassing more than 4 million tokens, across a spectrum of model families and scales. This includes Llama 2, 7, 13, 70, B, Falcon, 7, 40, B, Pythia, 2.8, 6.9, 12, B, and MPT, 7, 30, B. Section Summary. The proposed method for enabling LLM streaming in already trained LLMs involves reintroducing a few starting tokens KV in the attention computation, which stabilizes the attention computation and retains the most recent tokens crucial for language modeling. Additionally, the absence of a designated sync token to offload excessive attention scores can be remedied by including a global trainable attention sync token or using a variant of the softmax function that does not require attention scores to sum up to 1. Section 4.2 Results of Pre-training with a sync token. We wanted to test our idea that adding a sync token to all pre-training samples could enhance streaming language learning models, LLMs. To do this, we trained 2 language models, each with 160 million parameters, under the same conditions. One model followed the original training settings, while the other included a sync token at the beginning of every training sample. We used the Pythia 160M codebase and its training recipe for our experiments. The models were trained on an 8XA6000 NVIDIA GPU server using the Pile dataset, which had been deduplicated. We kept all the Pythia training configurations the same, except for reducing the training batch size to 256. Both models were trained for 143,000 steps. We found that adding a sync token during pre-training didn't negatively affect the model's performance. The models trained with a sync token showed similar convergence dynamics to the models trained without one. We tested the 2 models on 7 different NLP benchmarks, including ARC, Challenge, Easy, Hella Swag, Lambda, OpenBook QA, PIQA, and Winagrande. The model pre-trained with a sync token performed similarly to the model trained without one. However, we did notice a difference in streaming perplexities between the models trained with traditional methods and those trained with a sync token. The model trained with a sync token achieved satisfactory streaming performance using just the sync token, while the traditional model needed multiple tokens as attention sinks to maintain stable streaming perplexity. We also compared attention maps for models pre-trained with and without a sync token. The model without the sync token showed early layer local attention and deeper layer focus on initial tokens, similar to the Llama 2 to 7B model. On the other hand, models trained with a sync token consistently focused on the sync across layers and heads, indicating an effective attention offloading mechanism. This strong focus on the sync, with reduced attention to other initial tokens, explains why the sync token is effective in enhancing the model's streaming performance. To demonstrate the real-world applicability of StreamingLLM, we simulated multi-round question answering using instruction-tuned LLMs, which are commonly used in real-world scenarios. We concatenated all question-answer pairs from the ARC, Challenge, Easy datasets, fed the continuous stream to Llama 2, 7, 13, 70, B chat models, and evaluated model completions at each answer position using an exact match criterion. Dense attention resulted in out-of-memory errors, showing it's not suitable for this setting. While the window attention method worked efficiently, it had low accuracy due to random outputs when the input length exceeded the cache size. In contrast, StreamingLLM performed well by efficiently handling the streaming format, aligning with the one-shot, sample-by-sample baseline accuracy. We also introduced a dataset, StreamEval, inspired by the long-eval benchmark. Unlike Longeval's single query over a long span setup, we queried the model every 10 lines of new information. Each query's answer was consistently 20 lines prior, reflecting real-world instances where questions typically pertain to recent information. LLMs employing StreamingLLM maintained reasonable accuracy even as input lengths approached 120K tokens. In contrast, both dense and window attention failed at the pre-training text length and the KV cache size, respectively. We also used two context-extended models, LONGCHAT7BV 1.5 to 32K and Llama 2 to 7B 32K Instruct, to show that StreamingLLM can complement context extension techniques. In StreamingLLM, context extension means increasing the maximum cache size of streaming LLMs, allowing the capture of broader local information. Finally, we tested the effect of adding varying numbers of initial tokens with recent tokens on the streaming perplexity. The results showed that introducing just 1 or 2 initial tokens was not enough, but adding 4 initial tokens seemed to be sufficient, with additional tokens having only a marginal effect. This result supports our decision to introduce 4 initial tokens as attention sinks in StreamingLLM. Section Summary. The inclusion of a sync token during pre-training does not harm the model's performance, as demonstrated by similar convergence dynamics and comparable results on various NLP benchmarks. Models trained with a sync token achieve satisfactory streaming performance using just the sync token, while the addition of multiple tokens as attention sinks is required for models trained using traditional methods. The strong focus on the sync token, with reduced attention to other initial tokens, explains its efficacy in enhancing the model's streaming performance. Section: Cache Sizes. We're going to discuss the impact of cache size on the performance of StreamingLLM, a language modeling tool. You might think that a larger cache size would always lead to better performance, but our findings suggest otherwise. Surprisingly, increasing the cache size doesn't always result in lower perplexity, a measure of how well the model predicts a sample. This suggests that these models might not be fully utilizing the context they're given, which is an area that future research should focus on improving. Next, let's talk about efficiency. We compared the performance of StreamingLLM to a baseline method, the sliding window with recomputation, using the Hugging Face Transformers library and testing on a single NVIDIA A6000 GPU with the Llama 2 to 7B and Llama 2 to 13B models. Here's what we found. As the cache size gets bigger, StreamingLLM's decoding speed increases in a linear fashion. On the other hand, the baseline method's decoding latency increases at a much faster rate, following a quadratic pattern. This means that StreamingLLM is significantly faster, achieving a speedup of up to 22.2 times per token. What's even more impressive is that StreamingLLM manages to maintain a consistent memory footprint, even with its reduced latency. This means it uses about the same amount of memory as the baseline method, despite being much faster.